Okay, we left off with our mass matrix and our forcing vector in a symbolic form in MATLAB, in a format that MATLAB can use. But when I run this code, I get nothing because MATLAB needs numerical values for all of my parameters here. And just a reminder of what parameters we need here. If I go back to my PyDie code, I need here parameters, and I'll need a whole bunch of parameters later on, but for now I need parameters for the inertial properties of my body segments. The length of body segments A, B, and C. Remember, A is length of the trunk, LB length of the thigh, LC length of the shank. I need a length to the center of mass for each one of those segments. I need a mass for each segment. I need a moment of inertia for each segment. So a set of inertial parameters for each body segment. Now, where do I get those values from? Well, I could just make up any old values, right? I could say MA is, I don't know, 50 kilograms, and MB is, how heavy is a thigh? I don't know, 10 kilograms, and how heavy is a shank? I don't know, 5-ish. And then for LA, I could make up a trunk length, I don't know, maybe a meter or so. I could keep going here and just make up any arbitrary numerical values for these parameters. And that would allow me to run the code and fill these matrices with values, and I could do some calculations with them. That would be a fine way to test the implementation of the code and to verify the code. It's not a great way to model the human body. Remember, this is not just a set of equations, it's a musculoskeletal model. It's a set of equations representing the structure and function of the human body in a simplified form. So when I'm assigning values to these parameters, I don't just want to make up any arbitrary value. I want to assign values that are faithful to what's being modeled. For the mass of the trunk here, MA, I don't just want to assume some arbitrary value. I want to plug in a value that's realistic for the mass of the trunk. For the length of the trunk, I want to plug in a value that's realistic for the length of the trunk. So where can I get some realistic values for those segment inertial parameters? There's a lot of good sources out there. Most of them come from studies of human cadavers, which are sometimes maybe not the best data for us to use if we're simulating, say, a healthy able-bodied motion of, say, younger physically active adults, which we're doing a lot of the time. Those inertial parameters from cadavers will typically be from individuals who are very old and maybe not terribly healthy at the time of death, and so maybe not necessarily representative of the size and the shape of the bodies of younger, healthier individuals. One of the few rare exceptions to the sources or typical cadaver-based sources of those data is this paper here that I uploaded to the course website for you to take a look at, DeLeva 1996. This is a famous paper by Paulo DeLeva. I'd say it's probably maybe not necessarily the most widely used, but one of the most widely used sources for sure of body segment inertial parameters in biomechanics. DeLeva doesn't actually present any new experimental data here. He presents adjustments to some older body segment inertial parameter data, which were defined in reference to some kind of strange and unusual landmarks on the body. He adjusted them here to define them in reference to more typical anatomical landmarks of the body, and in particular have them defined in a way that's useful for us in defining parameters for musculoskeletal models. For example, here for my segment length LB, I want that specifically to be the length of the thigh, defined as the distance between the hip joint and the knee joint. And the original data here that he references from Zatsiorsky, Selyanov, did not have the parameters defined in that way, and so he adjusts them to define them in reference to those more common anatomical landmarks of the body in a way that's more useful for computer modeling. So DeLeva here didn't actually collect any new experimental data. He adjusted the parameter values reported in this older Zatsiorsky-Selyanov data set for body segment inertial parameters. This original study, the Zatsiorsky study, is a very famous study in biomechanics. It was done by Vladimir Zatsiorsky when he was a faculty member in biomechanics in the Soviet Union in, I believe, the 1980s. Zatsiorsky is one of the most famous biomechanists in modern times. He was actually one of Dr. Shim's doctoral advisors at Penn State. When he did this study, he was in the Soviet Union at the time. And again, this study is unique because it was not done on older human cadavers. It was actually done on live, healthy, young college-age physical education students in the Soviet Union, a group of men and a group of women. The study is a little bit controversial because you can see here the segment inertial parameters from the live human subjects were obtained by means of a gamma ray scanning technique. If you're into comic books, gamma ray scanning is how the Incredible Hulk became the Incredible Hulk. In real life, if you're bombarded by gamma rays, you don't turn into the Incredible Hulk, but you do get a massive dose of radiation. And some of these subjects later on in life went on to have some health problems that we think might have been related to the dose of gamma rays that they got when they participated in this study here. So the study, the original study, the Zatsiorsky study, has a little bit of a historical context and some controversy on how the data were collected and ethical treatment of human subjects and things of that nature. And so there is some controversy on whether we should actually be using these data at all. I do use them because despite some of the ethical issues involved, they are the most appropriate segment inertial parameters for using for representing healthy young adults when we're simulating those subjects and modeling those subjects. So this is a fairly dense paper. If you scroll down about halfway, the data are here in this image on page 1227 and in this table on page 1228. The image here shows you the average segment lengths and locations of the center of mass for the male subjects on average. On the left here is the original Zatsiorsky definitions of the segment endpoints, and on the right here is the adjusted values that Deleva came up with. And then if you scroll down here to table 4, it shows you the full data set for the female subjects on average F, and for the male subjects on average M here, showing you the length of each body segment relative to these endpoints here, the mass of each body segments relative to the fraction of their body mass, the position of the segment center of mass in terms of a fraction of that length, and the last 3 columns here, the sagittal R, transverse R, longitudinal R. Those are the radii of gyration of that body segment, again, relative to its longitudinal length here. For us, we're dealing with a two-dimensional model in the sagittal plane, so we're just going to use this sagittal radius of gyration here. A reminder from basic mechanics, if you take the mass of a body segment times the square of the radius of gyration, you get the moment of inertia of that body segment. And so with these parameter values here, with the length, the mass, the center of mass position, and the radius of gyration, we can calculate all the inertial parameters that we need to parameterize our musculoskeletal model. That takes quite a bit of work to do it manually. I already did it here, so I'll show you the results. Here I have an assumed, but let's paste this into MATLAB so you guys can see it a little bit easier. I'll call this 789W pars for parameters. And here I assumed a body mass M of my subject of 73 kilos, a typical healthy young adult male body mass. I then define my thigh as a fraction of that body mass. That number 0.146 is from the Deleva paper. My shank as another fraction of that overall body mass. The 0.0433 and the 0.0137 is the sum of the fractions for the shank and the foot. Remember, our shank here has the foot mass lumped in with it here. I then subtract those two masses from my overall body mass and assume everything left over is the mass of my trunk here. Notice here I multiplied my thigh mass by 2 and my shank mass by 2. This is because, remember, our model just has one leg here, and it's representing the two legs moving symmetrically, or kind of moving in the same way at the same time. And so I actually need to double my mass there to represent both of the thighs and both of the shanks. Okay, then I've got my lengths of each of my body segments, length of the trunk from Deleva's data there, length of the thigh, length of the shank from the knee to the ankle, and then this addition here is from the ankle to the floor, to the bottom of the foot. Values for my location of the center of mass, the distance from these joints along the length of the segment to the center of mass of that body segment, and then values here for the radius of gyration, and then from those masses and radii of gyration calculating the moment of inertia for those body segments. And then defining my environmental parameter down here, my gravitational acceleration. Okay, so I've got these parameter values saved in a script here. I named it Kines 79W pars.m. So I can go back to my equations of motion code and call that script up. Just type in the name of it here, and it'll run it and spit out all of my parameter values to my workspace here. Okay, so I ran it, and we still have a problem. Now I know all my parameter values here in my workspace, but I do not know my values of my time-varying quantities, my generalized coordinates, all the q's, and my generalized speeds, all the v's. Those are time-varying quantities. These will be states in the model when we do actual simulations of it. And so for here, for testing purposes, I'm just going to define some arbitrary values for them. So let's give it some generalized coordinates. Q1, remember, that's the horizontal position of the hip. We're just going to arbitrarily set that to 0. Q2 is the height of the hip above the ground. We'll set that to a meter above the ground. Q3 is the angle of the long axis of the trunk relative to the right horizontal. And let's set that to 80 degrees. Q4 is the hip angle. Let's set that equal to small flexion angle. And Q5 is the knee angle. We'll set that also equal to a small flexion angle. Okay. Let's just define all of our states here. And we're going to set all of our initial generalized speeds equal to 0. Okay, now, hopefully, unless I forgot something, when I run my code here, I should get no errors. And I indeed got no errors. And if I go to my workspace here, you can see that I've got numerical values for my mass matrix, my 5x5 mass matrix, and numerical values for my 5x1 forcing vector there. What do I do with those if I'm doing a forward dynamics simulation? I can divide the force by the mass and I can get the accelerations. And this will allow me to update my model generalized speeds, and I can use those to update my model generalized coordinates, integrating them forward in time over a small time step dt to calculate my new values for my generalized coordinates and generalized speeds. From those new values, I can then repeat the calculation of my mass matrix values, my forcing vector values, calculate new accelerations, and then update these states again for the next time step, and then iteratively repeat that process. Similar to how we were updating the states of the muscle model each time we went through that loop to calculate the force and the rate of change in activation and rate of change in CC length, using those rates of change to update those state values and move on to the next time step. Same process here with updating these model states for the equations of motion. Okay, that is it for this video. Next time we will do some actual work with these quantities in here, and we will do a little bit of plotting and animating of the model, and who knows, we may actually do an actual simulation of the model.